In order to achieve the greatest velocity possible, spacecraft fitted with a solar sail must fly as close as possible to their nearest star in order to maximize sail reflectivity and absorptivity. However, as we might expect, the distance of closest solar approach is affected by the chosen sail material's ability to withstand the harsh solar environment. Past research investigates flight trajectories and finds that a perihelion of 0.1 astronomical units would cause the solar sail and spacecraft to experience 100 times the solar irradiance that it would at Earth, where the perihelion is the distance of closest approach between the spacecraft and the Sun, and the astronomical unit is a measure of the distance from the Sun to the Earth, where 1 astronomical unit is that distance. Of course, passing by the Sun at 0.1 astronomical units can be beneficial for acceleration, but can lead to sail heating and damage. The current generation of solar sails are made up of a 100 nanometer thick aluminium layer integrated with a micron thick polymer layer, and this diagram here represents just that. However, this design has a limitation, which this figure from Davayan demonstrates. We see that as the distance to the Sun decreases, the temperature experienced by the solar sail increases exponentially. This is of course to be expected, but the issue arises from the materials currently utilized. Common polymers used, such as mylar and Kapton, have melting temperatures indicated by the horizontal dotted lines. This limits closest solar approach to 0.125 AU for mylar and 0.075 AU for Kapton. Kapton-based sails can get closer to the Sun due to their higher melting temperature, but they are much thicker and heavier than mylar films. Hence, thinner mylar films are commonly used. Additionally, currently utilized levels of emissivity, that is, a material's effectiveness in emitting energy as thermal radiation, are quite low, meaning that regardless of melting temperatures, present-day solar sails are limited to distances greater than 0.4 AU from the Sun, which significantly impacts speed capabilities. By increasing the backside thermal emissivity, that is the emissivity of the sail surface facing away from the Sun, missions as close as 0.2 AU could be possible and would be achieved through carefully tuning infrared spectral properties of polymer materials. For approaches closer than 0.2 AU, further development of high-temperature materials is required. A concept known as the metallized sail is a potential solution in overcoming the associated temperature issues and is therefore useful in interstellar flight. This sail design resembles currently used polymer designs with a thin layer of metal on the sun-facing side. But by replacing the low-temperature polymer with a high-temperature material, the operating temperature of the metallized sail would be approximately 900 Kelvin, which can significantly improve acceptable perihelion distances.